With this video, I start a playlist on special functions. We've done all kinds of things so far, talking about polynomial equations, algebraic equations, talking about differential equations, and all manners of equations. But then, a time comes where you get to see some kind of functions that are not the regular types you're used to, and that is the necessity for special functions. So, well, maybe this may be your first time of hearing about special functions, or maybe you've seen some types of special functions without knowing uh, what they are called. So this is the opportunity to get into this flow. Special functions, of course, form one of the most important areas of advanced mathematics, mathematical physics, engineering, and applied sciences. They arise naturally when ordinary algebraic and elementary functions are insufficient. So, like I said the other time, there are sometimes all those algebraic and elementary functions, become insufficient for solving differential equations that model physical systems. So special functions are deeply connected to things like differential equations, mathematical physics, orthogonal systems, eigenvalue problems, coordinate systems, boundary value problems. And interestingly, I've dealt with almost all of these types of issues in previous playlists. So examples of special functions. So at this point, maybe you have come across one or two special functions before. So we have the Bessel functions, Legendre polynomials, Hermite polynomials, Laguerre polynomials, gamma functions, and of course hypergeometric functions, which are really very important. So these functions appear repeatedly in physics, in engineering, in probability theory, and applied mathematics. So let's go straight to see what special functions are. What are special functions? A special function is a function that one appears repeatedly in mathematical and physical applications, and then it's the function that satisfies an important differential equation. So you can simply say that special functions satisfy they satisfy important differential equations. Then a special function possesses rich analytical properties, as you're going to find out, and a special function is usually cannot be expressed in terms of elementary functions. So you'd be wondering what elementary functions are. You get to see elementary functions very soon. So elementary functions include, of course, this is it right here. Elementary functions include polynomials, exponentials, logarithms, trigonometric functions, and inverse trigonometric functions. These are like elementary functions. So, and that brings me to the idea of a kind of categorization of functions, right? So, generally speaking, before now, you can categorize. So say you have functions, right? You have functions. So you can categorize functions into two, if you like. You can categorize them into elementary, elementary, elementary functions, and special functions. Okay. Now, if you want to go further, you can categorize elementary functions into two again. So you can categorize elementary functions into polynomial functions, polynomial functions, and what you know as transcendental functions. Transcendental functions. All right. So if you want to give examples of this, right? This is you can go this way. Polynomial functions, of course, things like you have linear functions, you have linear functions, you have quadratic functions. And of course, you can have cubic and all that, but I can just say higher functions. On the other hand, when we talk about transcendental functions, we're talking about things like logarithmic functions, logarithmic functions. They are not polynomials, logarithmic functions. Then you have things like trigonometric functions, trigonometric functions. You have inverse trig, things like that that are not polynomials. But thankfully, you can actually have okay, let me just say inverse trig, right? Inverse trigonometric functions. These are all transcendental. So they are not polynomials. But thankfully, with the help of with the help of Taylor series, you can bridge the gap between transcendental functions and with Taylor series, right? Transcendental functions can be converted to can be approximated as polynomials, and we've used that a couple of times. So Taylor series, okay? So with the help of Taylor series, you can approximate transcendental functions as polynomial functions. So functions can be generally classified as elementary functions and polynomial functions and special functions. Another elementary functions, you have polynomial functions and transcendental. So you know polynomial functions, they can be expressed as terms, sum of terms, multiply, you have a coefficient multiplied by the variable and an integer power, right? So, but transcendental functions are every other function that are not like that. But any function that is not polynomial or transcendental can then be said to be a special function, which this playlist is basically about. So examples of elementary functions are things like, we said polynomials like x squared, x cubed, x raised power 7, whole number power, basically. And then you have exponentials like e raised power x, 2 raised power x, and logarithms like ln x, that's log e base x, log then base x, trigonometric functions like sin x, cos x, tan x, or inverse trig, maybe arc sine of x, or inverse arc sine of x, arc cos of x, and all of that. These are elementary functions. So special functions then go beyond these elementary functions. So special functions are functions that cannot be expressed in terms of all these elementary functions that have been listed. For example, you have the Bessel function, which is denoted as J naught of x, which cannot be generally written using elementary functions. So it has its own special properties. So let's talk about a bit of history. We have the historical development of special functions. So special functions emerged naturally from physical problems. So some important historical developments include the following. You have Legendre, who was a scientist that came up with the idea of Legendre polynomials. You have Bessel, who came up with Bessel functions. You have Hermite, who came up with Hermite polynomials. Laguerre came up with Laguerre polynomials, and Fourier, who came up with Fourier series. Now you see that most of these scientists they were either French or German for the most part. So originally, these functions were discovered independently while solving problems in areas like astronomy, heat conduction, electromagnetism, acoustics, quantum mechanics. Later, mathematicians discovered deep unifying structures among them. So the question now is, why elementary functions fail? Why do elementary functions fail at some point? Elementary functions are often insufficient because many physical systems obey differential equations whose solutions are more complicated. So consider this system, the simple differential equation y prime prime plus y equals 0. Its solutions are elementary. Like, when you solve this, you get the uh what is it called now? There's a party you get an expression from it that's m squared plus r, and you solve it, and by the time you're done with that, you get y to be a cos x plus b sine x. However, more complicated equations arise in realistic physical systems. So you can actually express the solution of this differential equation in terms of elementary functions, which are trig in this case. So, but more complicated equations arise in realistic physical systems. So let's talk about a very good example, which is the Bessel's equation. Now, consider the equation x squared y prime prime plus xy prime plus x squared minus n squared y equals 0. I treated this a lot when I dealt with differential equations, differential equations with variable coefficients. So this is called the Bessel's equation, and its solutions are j sub n of x. So the solution is a family of functions called the Bessel functions, Jn of x. So this n can mean j1, it can be j0, j0 of x, j1 of x, and so on and so forth. So, and we also have the yn of x, which are called the Bessel functions. So the jn of x are Bessel function of the first kind, while yn of x are Bessel functions of the second kind. So these solutions cannot generally be expressed using elementary functions. And this demonstrates why special functions are necessary. So special function fails in certain situations, especially when you cannot express the solutions to certain differential equations in terms of elementary functions like polynomials, logarithmic functions, exponential functions, and so on and so forth. Now let's talk about physical origin of special functions now. Special functions emerge naturally from geometry. So different coordinate systems produce different special functions. So we have seen that special functions come about when you are looking for solutions to some differential equations, and those solutions cannot be expressed in terms of elementary functions. Then now we are seeing that special functions emerge naturally from geometry. So different coordinate systems produce different special functions. So the most common coordinate system we are used to in mathematics would be the Cartesian coordinate system, where you have the x and y axis, right? But so the Cartesian coordinate system produces trigonometric functions as special functions. The cylindrical system, the coordinate system produces Bessel functions, and you have the spherical coordinate system, which leads to Legendre functions. And in the parabolic coordinate system, you have Hermite functions. Thus, geometry determines the mathematical structure of the solutions. Okay. Now let's look at example of non-elementary integrals. So imagine, consider this integral now, integral of e raised to minus x squared dx. Now this looks like something you can easily deal with very easily. For instance, if I make it like x e raised to minus x, things become a bit easier. You know, if I have this, if I have like integral of x e raised power minus x squared dx. So it will be a bit, it will be totally different, right? Because I can just say let u be x squared. That implies that du dx is equal to 2x, meaning that, you know, because there's dx here, because we are changing everything in terms of u now. So it means that du is equal to 2x dx, meaning that dx itself will be divided by 2x. So that dx will be du over 2x. So with that in place now, we can then come over to the integral. So integral of x e raised power minus x squared dx then becomes integral of x dot e raised power minus u, because x squared is u, times dx. Dx now is du over 2x. So x cancels x, and then we have integral of e raised power minus u over 2 du, which can then be written as half into e raised power minus u du. So if you now integrate this, we have half. If you integrate e raised power minus u, that's e raised power minus u plus 1 all over minus u plus 1. You know, uh, yes. Okay. No, this is an exponential expression, so I can't just do it like that. So to integrate this, right? So differentiate minus u, you get minus 1. So this is like e raised power minus u all over minus 1, yeah? Plus a constant c. So this is now half into minus e raised power minus u plus c. So if you tidy all of that up, minus can come. So you have minus half e raised power minus u is now x squared plus c. So this is what you get in that case. But when you have integral of e raised power minus x squared dx, now things become more complicated than what I just did up there. So in this case now, so we have non-elementary integral. An elementary integral is an integral whose solution is simply elementary, right? You can just get the answer. So consider the integral e raised to minus x squared dx. This integral cannot be expressed using elementary functions. Therefore, mathematicians defined a new function called the error function. So to get an answer to this, the error function was defined. So the error function of x is given as 2 over square root of pi integral 0 to x e raised to minus t squared dt. So the error function appears in probability theory. In fact, that's the whole basis of Gaussian, of the Gaussian or normal distribution. Then it appears in statistics, in heat conduction, in diffusion processes. So, and we have that kind of thing here. So the error function comes, it's like a saturation function like you see here. So we need num-pi, matplotlib, and scipy to get the error function. So I think, in fact, I got my inspiration for to teach special functions when I was doing scientific computing with Python. And we got to that point where we're dealing with scipy. So there's a library in scipy called scipy special, and this is exactly the library here. Scipy, or if you like, call it a module. Scipy is the library. The special module is under SciPy. So you have SciPy the special, and for me, it's one of the special functions defined is the error function. So once you define the error function over minus 3 to 3, so this is how it looks like a saturation kind of expression like this. So, and then we go on to talk about differential equations and special functions now. So most special functions are defined as solutions of differential equations. So both special functions are solutions of differential equations. A general second order linear differential equation has the form a2 of x y prime prime plus a1 of x y prime plus a naught of x y equals 0. Depending on the coefficient, the equation may produce either elementary solutions, which we are very used to, or special function solutions like that. So let's look at the Legendre equation for instance. The Legendre differential equation is 1 minus x squared y prime prime. So in this case now, a2 of x is 1 minus x squared y prime prime, then minus 2x y prime. So a1 of x now is minus 2x, then a naught of x is now n into n plus 1, then multiply by y equals 0. So the solution to this kind of equation, which is called Legendre, its solutions are the Legendre polynomial. So Legendre polynomials are solutions to Legendre differential equations. So you have Pn of to the Legendre differential equation, right? So and they are generally given as P sub n of x. So these functions appear in electrostatics, in gravitational fields, in spherical harmonics, and quantum mechanics. Then we have the Hermite equation. So the Hermite differential equation is y prime prime minus 2xy prime plus 2ny equals 0. Its solutions are the Hermite polynomials h sub n of x. So you have Hermite polynomials as solutions to the Hermite differential equation. Now these are called Hermite polynomials because depending on the value of n, you can have as many as possible. So applications include quantum harmonic oscillator, probability theory, and Gaussian quadrature. Then we have 1.10, the Laguerre equation. So the Laguerre differential equation is xy prime prime plus 1 minus xy prime plus ny equals 0. So its solutions are Laguerre polynomials L sub n of x. And these have applications in hydrogen atom, laser optics, and quantum mechanics. Then we talk about separation of variables, which is one popular technique. We saw this when I dealt with differential equations, both ordinary and partial differential equations. One of the most important methods producing special functions is the method of separation of variables. So if you consider the heat equation partial u partial t equals c squared partial squared u partial x squared, of course, this is both space and time because heat spreads in space and in time. So T is time, X is space, like maybe the length of a rod or something like that. So if you assume a solution of the form U of X comma T, that is the heat form, U of X is U of X comma T equals X of X multiplied by T of T. So now you have decomposed that solution, the heat, into the product of space and time, like that. So according to that, you can then apply separation of variables. So if you substitute u of x comma t, comma t equals x of x times t of t into the heat equation, the original heat equation. So this partial u partial t, now that means you differentiate this with respect to t. So you get x t prime equals c squared, then so you have c squared, right? The partial squared, u partial x squared will now be x prime prime t because t remains constant. So you differentiate it first time x prime, second time x prime prime. So you have this. So you can then divide both sides by xt. So that's the separation of variable part there. So you have t prime all over t equals c squared x prime prime over x. The left side depends only on t. So this side depends only on t, while the right side depends only on x, as you can see. So we have separated the variables at the time and space variables into two parts. So therefore, both must equal a particular constant. So it means that t prime over t equals c squared over x prime prime over x must be equal to minus lambda, must be equal to a constant minus lambda. This produces two ordinary differential equations, which are, if t prime over t is equal to minus lambda, so that means if you multiply 3 by 2, you have t prime equals minus lambda t. And then if you put it together, you have t prime plus lambda t equals 0. On the other hand, I mean, I did this extensively under the partial differential equation playlist. So for this other one, if you have c squared x prime over x equals minus lambda, you can end up having x prime prime plus lambda over c squared x equals 0, like this. So you have these two ordinary differential equations that can now be solved easily. So you have that. So importance of geometry here. If you define geometries, different geometries rather produce different ordinary differential equations after separation of variables. So Cartesian produces sine and cosine, cylindrical produces Bessel, spherical produces Legendre, parabolic geometry produces Hermite. The special functions are strongly connected to symmetry and geometry, like we said earlier. So now we have Laplace equations in polar coordinates. Okay, so we have Cartesian coordinates x and y. Polar coordinates, you have r and theta. So, and you can convert from one coordinate to another. So, if you consider Laplace's equation, is it del now? Del squared u equals 0. In polar coordinates, that becomes partial squared u partial r squared plus 1 over r partial u partial r plus 1 over r squared partial squared u partial theta squared equals 0. So, if you assume that u of r comma theta is r of r, theta of theta, after separation of variables, we obtain r squared, small r squared, small r squared, big R prime prime plus small r, big R prime plus small r squared lambda multiplied by big R equals 0. And this becomes the Bessel equation in the polar coordinates like that. So we can deal with this. So if you look at this now, for the code now to get Bessel function, so you need NumPy and the regular things we need now, but you have to import JV. JV talks about Bessel of first kind, and YV is Bessel of second kind, as we're going to find out later. So, so over 0 to 20 in 500 divisions, that is the figure size. So for n in range 4, so this Bessel function is J sub n of x, right? So when n is 0, 1, 2, 3, range 4 means you do up to 3, right? 0, 1, 2, 3, like that. So, and then you plot x against the Bessel functions for n and x. So the n values have been changed here, and then you label it based on whatever n you're dealing with in that case. So you can then so you have the title Bessel function. So if you run this now, you end up getting these Bessel functions. So okay, I can do it step by step. If I have this to be 1, let's see if that works, right? So if it is 1, this is what you get. This is Bessel function, of first kind, evaluate at n equals 0. This is what you have like that. And then if I increase it to 2, so I have 0 and 1 now. So you have J naught of x and J1 of x. So you can see it's there's a kind of shift in phase like that. Then I can, make it 3 now. So I can increase it to 3, and then this is what we get. So it looks like another phase shift for the orange. So it moves, so the peak, so this one starts from here, the peak moves there, and then the green one goes like that. So we can also make it, if this is 4 here, there's also a shift like that, which we have this red now. Okay, so you see the peaks are just falling like that. And then of course, let me go as far as 5, meaning that we have 0, 1, 2, 3, 4. So you have the purple one now. So you see the peaks are gradually falling like that. Okay, so that's Bessel there of first kind. Now, of course, we are going to deal better with the Excel functions as we go on. This is just an overview of everything. Now, classification of special functions. Now, how do you classify special functions? Now, special functions can be classified in several ways. First of all, they can be classified by differential equation. So the Bessel equation gives you Bessel equation functions. Legendre equation results to Legendre polynomials. Hermite equation, which is a differential equation, leads to Hermite polynomials as special function. Then you have Laguerre equation leading to Laguerre polynomials. So you can classify the special functions by the differential equation they come from. Then you can also classify by orthogonality. Many special functions form orthogonal systems, right? Then you can classify by integral representation. Many functions can be represented as integrals. Like the error function now, you can represent it as integral like we saw before. Then classification by generating functions. Some functions are defined through generating functions. We're going to see all of this one after the other as we go on in this playlist. So many special functions satisfy orthogonality relations. So for Legendre polynomials, right, integral from -1 to 1 of Pm of x, Pn of x dx is equal to 0. That's the idea of orthogonality, that when you integrate two different Legendre polynomials, for m not equal to n. So if you integrate from between -1 and 1, you get 0. So orthogonality is extremely important in Fourier analysis, quantum mechanics, signal processing, and approximation theory. Okay, orthogonality is a key concept you're going to come across a lot. Then we talk about generating functions. So special functions often possess generating functions. So generating function, as the name implies, is a function that generates a family of polynomials or a family of whatever you're working with. So, in fact, I have a playlist on generating functions, and generating functions are often very connected to probability and statistics. So, for Legendre polynomials, right, the generating function is given as 1 over square root of 1 minus 2xt plus t squared, and that leads to summation from n equals 0 to infinity of p sub n of x t raised power n. So, of course, this one you can actually expand it in a binomial series, and then you end up getting something like this. So generating functions are useful because they encode infinitely many functions into a single formula. So you have a generating function is a formula that encodes many functions in it by just, so in this one, I might just put in the values of n. Things keep increasing like that. Okay, so let's talk about the Rodrigues formula. Many orthogonal polynomials possess Rodrigues formulas. So for Legendre polynomials, for instance, p sub n of x, like this p sub n of x you see here, can be expressed as 1 over 2 raised by n factorial, uh, nth derivative, dn dx power n of x squared minus 1 raised power n. So Rodrigues formulas provide explicit construction methods. Then we have integral representation of Bessel functions. So Bessel functions possess the integral representation j sub n of x, and that is equal to 1 over pi integral from 0 to pi cos n tau minus x sine tau d tau. So integral representations are important in asymptotic analysis, numerical computation, and complex analysis. Then we have the gamma function. Okay, that's one of the earliest functions to be seen as we study special functions. The gamma function generalizes the factorial function. So the gamma function has something to do with factorial functions. By definition, the gamma of x is given as integral from 0 to infinity, t raised power x minus 1, e raised power minus t dt. So this is another special function that can be represented in integral form. So for positive integers, then we have the gamma of n to be n minus 1 factorial. You're going to see why this is in subsequent videos. An example of this will be gamma 1 over 2 is equal to root pi. We are going to prove that in the course of this playlist. I think in the next video we should deal with gamma function explicitly. Okay, so, and from there to be sure that that is actually true, that gamma of 1 over 2 is root pi. So we can confirm that here. So we just, from sci pi to special, we have gamma. And if you take gamma of 0.5, you get 1.7724, which is square root of pi. Same, if you just now say square root of pi directly, you get the same result exactly. So that establishes the fact that gamma of 1 over 2 is square root of pi. Then we have beta function, which is the next, which will be treated in the video after gamma function. So for beta function, it can also be expressed as an integral. So the beta function is defined by b of x comma y equals integral from 0 to 1, t raised power x minus 1, 1 minus t raised power y minus 1 dt. So the beta and gamma functions are related by, so there's a connection between beta function and gamma function in that the beta of x comma y is equal to gamma of x multiplied by gamma of y, all divided by gamma of x plus y. We are going to prove this too when we get there. Then we have the hypergeometric functions. Many special functions belong to the hypergeometric family. So the hypergeometric differential equation is x into 1 minus x y prime prime plus c minus a plus b plus 1 x multiplied by y prime minus aby equals 0. So this is a general the family of geometric differential equations. So depending on whatever a and b may be. So its solution is the hypergeometric function 2f 2f sub 1 into a comma b full colon c full colon x. Many classical special functions are special cases of hypergeometric functions. So you see how important hypergeometric functions can be put together so many other things. So many classical special functions are special cases of hypergeometric functions. Then we talk about relationships among special functions. Now, many special functions are interconnected. So, for instance, you have the Legendre function is connected to the hypergeometric connection of Legendre is hypergeometric. Hermite is confluent hypergeometric. Laguerre, confluent hypergeometric, and Bessel is also confluent hypergeometric. This reveals a deep unifying mathematical structure. So the hypergeometric functions are like a big umbrella for other special functions, like said already. Then we talk about the Sturm-Liouville theory. So Many special functions arise from Sturm-Liouville problems. The general form will be d dx of p of x dy dx plus lambda wx minus q of x multiplied by y equals 0. These problems produce orthogonal eigenfunctions, discrete eigenvalues, and complete function systems. So, and then what with the physical interpretation? Special functions often represent physical modes of vibration, and examples include vibrating strings, electromagnetic waves, quantum states, heat distributions. Orthogonal functions behave like independent vibration modes. So, and then we talk about numerical computation of Legendre polynomials. Scientific computing libraries provide implementations of special functions. So you have Python libraries including SciPy, NumPy, SymPy, and MPMath. So here now we have legend polynomials represented here. And just like what I did the other time, so we can begin. So this is what it looks like for from P naught to P4. So all I'm going to do is I'll keep changing this like I did the other time. So if this starts from one, well, let me even try zero and see what happens. This is going to be probably be an error thing. Yeah, so nothing is showing because it's zero. So no artists will with labels found to be put in legend. That's okay. But then I have one now, which gives us the first one. Okay, so we have just a straight line drawn at 1.0. Okay, then we have, so if you take this to 2, then we have another line, you know. So now you have a line slanting from minus 1.0 to 1. So like a diagonal like that. And then we have, if I take it to 3, we have something, we have a third line, okay, which is not like, which is, that looks more like a parabola. Is it hyperbola? I think it's more like a parabola sitting on 0.00. And then we go to 4. So for 4 now, we have a folding. So you have a curve with two peaks, with a maximum and minimum like that. And then if I go to 5 now, you have a curve with three minima and maxima together, three extrema. So you have this minimum here, maximum, and another minimum like that. So that's how Legendre polynomials actually go like that. All right. So, and the what is bringing that out is eval underscore legendre. That's what is bringing all of that out. And then we go for the conceptual structure of special functions. So this is like the overall concept of special functions. A useful conceptual hierarchy will be from differential equations, we have eigenvalue problems. Eigenvalue problems lead to orthogonal functions, and orthogonal functions lead to special functions. And we see that geometry and symmetry determine which special functions appear at the end of the day. In summary, then, we see that special functions arise because elementary functions are insufficient for solving many important differential equations. Major ideas include differential equations generate special functions, separation of variables produces canonical equations, geometry determines the function family, orthogonality plays a central role, and hypergeometric functions unify many families. And then we see that important families include the following: Bessel for cylindrical systems, Legendre for spherical systems, Hermite for quantum oscillators, Laguerre for hydrogen atom, gamma for generalized factorial, and hypergeometric for unified framework. So the final perspective we see then is this. We see that special functions are fundamental because they encode symmetry, geometry, boundary conditions, physical laws. They form the mathematical language of the advanced physics, engineering, and applied mathematics. Understanding special functions provides deeper insight into differential equations, mathematical physics, spectral theory, quantum mechanics, and applied analysis. So we come to the practice problems. So of course, I'm going to solve two of this. So see problem one right there. I'll be solving problems 4 and I think problems 4 and let me see, problems 4 and 9. Yeah, I'll be dealing with 4 and 9. Okay, so show that the function y equals a raised power x, y equals e raised power ax satisfies the equation. This, of course, all you just do there is differentiate this. You need y and its derivative. So differentiate this and put it here minus a times what it's here. It should evaluate to 0 very easily. Problem to verify that y is cos nx is a solution of this. Of course, differentiate this twice and put y here, put the second derivative here, and everything should go to 0 normally. Then you have problems 3, 4, and 5 now. Determine whether the differential equation, this has variable coefficient or constant coefficient. Of course, this x squared is a variable coefficient. 3x is a variable coefficient, so it has variable coefficient. Then problem 4, show that the gamma function satisfies this. Of course, we are going to prove this in the next video because that is totally on gamma functions. Then I think this is what I'm going to be, okay, this is the first problem I'll be solving here. So I'll be dealing with this. And of course, we still see it later. Then problem 5, evaluate gamma 5. Of course, we know this to be 4 factorial, and that is simply 24. Then you have problem 6, compute beta 1 comma 3. We've not really done it, but I mean, using the integral, you can deal with it. Then problem 7, use the gamma beta relation to evaluate B22. Then problem 8, find the first three terms of the power series expansion of a raised to minus x squared. Of course, well, you know the idea of power series already. Determine, because I did a playlist on it. In case you don't know, you can check that up. Then determine whether the following functions are orthogonal on the closed interval -1 and 1, f of x equals 1 and g of x equals x. Then you have problem 10, 11, 12. So show that P naught of x is 1 and P1 of x is x. Satisfy the Legendre differential equations. Problem 2, find the Rodrigues formula expression for P2 of x and simplify the result. And problem 12 now, this is problem 11. So problem 12 is to verify that H1 of x is 2x. Satisfy the Hermite differential equation for n equals 1. Then problem 13, 14, 15. Use the Laguerre differential equation to verify that L naught of x is 1 is a solution. Then classify each of the following as elementary or special. Sin x is elementary, ln x is elementary. This is Bessel. J naught of x is not elementary, it is actually special. Gamma of x is special also. Then e raised power x is elementary. Elementary functions are basically polynomials, trigonometric functions, logarithmic functions, and exponential functions. Any function like such functions. So like I said earlier, functions can be classified broadly into elementary functions and special functions. And elementary functions can be further classified into polynomial functions and transcendental functions. So sin x, ln x, e raised by x are all transcendental functions. So polynomial functions will be things like x squared, x cubed, and so on. Then problem 15, explain why cylindrical symmetry naturally leads to Bessel functions. You're going to see that when we deal with Bessel. Then you have 16, 17, 18 now. Explain why spherical, okay, we've said that. 17, 18, let me see if we can fit everything at once. Okay, let me go gradually here. So find the separation constant after separating variables in this. You have u of x comma t. I think the kind of thing we did the other time exactly the same, except that the notation u sub t here is partial u partial t, while u sub xx is partial squared u partial x squared. Then you have problems 18, 19, and 20. So determine whether the following differential equation is linear or non-linear. Y prime prime plus x y prime plus y equals sin x. Problem 19, find a weight function associated with Sturm Liouville equation. Of course, I didn't teach enough in this video for you to handle this, but I mean, you want to take it as a challenge or wait until I do something like this. Just follow along in the playlist. Then, so you have a kind of research problem now. Investigate one application of special functions in physics, engineering, or probability theory, and write a short summary discussing the differential equation involved, the special function obtained, the physical interpretation, and why elementary functions actually fail in such an instance. So let me go ahead and do the two problems I promised to take care of before we bring this to a close. So, like I said, I'm taking care of problem 4. I'm solving problem 4. So, problem 4 now. The problem statement is to show that the gamma function, the gamma function satisfies, show that it satisfies gamma n plus 1 equals n gamma n, like this. Or let me do it the way it looks here. I'm used to doing it this way, but so gamma n plus 1 equals n gamma. I need to unlearn what I've always known. So gamma n like this, using integration by parts, using integration by parts. So this is going to be a bit lengthy, but let's go for it. So let's go. We have first of all, you start with definition of the gamma function. So we know that the gamma function, the gamma function is defined by gamma n plus 1 equals integral from 0 to infinity x raised power n e raised power minus x dx. That's how the gamma function is defined. So we now apply integration by parts. Okay, so applying integration by parts, applying integration by parts. So we see here that, so for integration by parts, you pick a function that when you keep differentiating, it goes to a constant at the end of the day. And this is what that looks like. So for integration by part, generally, we know that it is integral of u dv is equal to uv minus integral of v du, right? So in this case now, we have to pick our u. Since you have u here and du here, it means you want to pick something that if you keep differentiating, it goes to a constant. So this is better as u, and the rest of this is better as dv. So if that is the case, then we can have that we can say let u be x raised to power n. That implies that du dx is equal to nx raised to power n minus 1. That's bring down the power and reduce the power on top of x. So that means du itself is n x raised to power n minus 1 dx. So that is settled there. On the other hand, we let dv be e raised to power minus x dx, just like I pointed out here. That's all dv. So we have dv here, but then we have v here. It means we have to integrate that to get v. So that's integral of dv now equals integral of e raised to power minus x e raised to power minus x dx, right? So that means v on its own is, when you differentiate e raised to power minus x, you should get minus e raised to power minus x plus c, or you can be silent about this right now, because at the end of the day, we'll still put the plus c. So you have this now, and you have this also. So with that in place now, we can then go ahead and talk about, we can then apply integration by parts. So we can say, so integral of u dv equals uv minus integral of v du. So that means we have that gamma n plus 1, gamma of n plus 1 now is equal to uv. So what is our u? U is nx raised by n minus 1 dx. Okay, so that's u. Okay, u is xn, sorry. U is xn. Normally this is integral from 0 to infinity, right? So we have xn, and v is minus e raised to power minus xn. All of this from 0 to infinity, minus integral of v. V is minus e raised to power minus x. All right. Then du, or rather dv. No, it should be v du. So du. So our du is nxn minus 1 dx. So that is n x nx raised by n minus 1 dx now. So we can tidy things up here. So this is integral. Well, we can put the minus outside, I believe. So we can put the minus outside. So this is, let's put this outside. So x raised by n, e raised by minus x from 0 to infinity, minus, okay, minus and minus plus n comes out, then integral of e raised by minus x raised by n minus 1 dx. So with this now, we then have, so if you put the infinity here, so it's more like you have minus infinity raised by n, e raised by minus infinity, minus, that's representing x. So 0 raised by n into e raised by minus 0. So all that plus n, of course, from 0 to infinity also, integral e raised by minus x, or better still, x raised by n minus 1, e raised by minus x dx. Okay, so of course, e raised by minus infinity goes to 0, and 0 times anything also goes to 0. So all this part goes to 0. So we then have integral n so we now have gamma n plus 1 now to be n there, integral from 0 to infinity, x raised by n minus 1, e raised by minus x dx. Now, this looks familiar, right? Because if you remember where we're starting from, x raised by minus n, e raised by minus x raised by n minus 1 rather, x raised by n minus 1. Oh, okay. Um, something is happening here. Okay, x raised power n, yeah. Okay, great, great, great. X raised power n. Okay, I think there's something we need to take care of. 0 to infinity. So it's x raised power n minus 1, e raised power minus x. X raised power n minus 1, e raised power minus x. So this power of n, there's something about it we need to put in order. X raised power n minus 1. The original expression is x raised power n, right? Um, okay, now that's fine. That's great. So based on the definition of uh, gamma function, right? Normally, gamma n plus 1 is x raised power n. So if you're going to deal with, if you have gamma n, it has to be n minus 1. So it means that this is now n gamma n, basically. And that's what that's the deal here. So n gamma n. Maybe I should just still stick to how I've always done it. So in essence, now we have come to that point now. So we see that this part is basically, if gamma n plus 1 is x raised power n, e raised power minus x, then gamma n itself will be x raised power n minus 1. So we have seen that part now. We can say, so gamma gamma n plus 1 is actually n gamma n, basically. N gamma n. Yeah. And that's exactly what that looks like. Okay, the other solution I said it was 9. And the other problem I'll be solving is 11. Let's say what's problem 11 now? Let me see that. Problem 11. This is okay. Find the Rodrigues formula expression for P2 of x and simplify the results. So let's quickly take care of that as we bring this to a close. Okay, so I guess I want to change markers here. I've missed green a lot. So I guess this can go for green. Green can come now. Yeah. So problem 11, that's the second problem we're solving here. Problem 11. Okay. So we have the problem statement. Find, want to find the Rodrigues, find the Rodrigues formula expression, Rodrigues formula expression for P2 of x and simplify the results and simplify the results like that. So we go for the first step. So step 1. Okay, let me just not bother about the steps, right? So the first thing, the Legendre polynomial, the Legendre. So we're trying to remember the Rodrigues formula now. The Legendre polynomial satisfies P sub n of x equals 1 all over 2 raised power n factorial dn dx raised power n into x squared minus 1 raised power n. So for n equals 2 now, okay, notice the general formula. So for n raised power 2, we then have p2 of x equals 1 over 2 raised power 2, 2 factorial d squared dx squared into x squared minus 1 raised power 2. So all the ends now will now be 2 because we are dealing with p2 of x. You know, p2 of x here means that n is equal to 2. So with that in place, then we have to simplify. So we know p2 of x here is then 1 over 2 raised power 2 is 4. 2 factorial is 2. Then d squared dx squared of x squared minus 1 raised power 2. So like that. And then so we need to simplify, right? So this is at a level. Let's keep going. Then we then have p2 of x. P2 of x now is equal to 1 over 8. Well, we can do some gymnastics here. Maybe to make things still easier here, we can say d squared x dx squared. And that will be, so we can expand this whole thing straight up. So since we are squaring, that'll be x squared squared. minus 2 into x squared times 1 plus 1 squared, like that. So we then have 1 over 8 d squared dx squared. So this is x raised to power 4 minus 2x squared plus 1. That's what that looks like. And then we have 1 over 8. So d squared dx squared means we are differentiating two times. So it means that we can have d dx of d dx into x raised to power 4 minus 2x squared plus 1. So we differentiate first time. So we have 1 over 8 d dx of, when you differentiate that, you get 4x cubed minus 4x, right? Minus 4x, yeah. 1 is constant, so it goes away. So that's step 1. So next step now, we can have P3 of x. I mean, P2 of x now is still 1 over 8. Then we differentiate the second time. So differentiate 4x cubed, we get 12x squared. Differentiate 4x, we get 4. So we can tidy things up a little bit by simplifying. So we simplify and we get 1 over 8 into, okay, 4 is common, right? So 4 into 3x squared minus 1. So 4 over 8 is 1 over 2. So we have 1 over 2, 3x squared minus 1. So, so P2 of x, which we want, is 1 over 2 into 3x squared minus 1. So we see that this polynomial appears frequently in electrostatics, gravitational potentials, spherical harmonics, and quantum mechanics, as mentioned earlier. So that's that about uh the second problem here. So that was asking us to find the Rodrigues formula expression for P2 of x and simplify the results. And that's what we've done here. So we get the original expression. Since P2 of x is what we're looking for, n is 2. So we fix 2 and we end up getting 1 over 2, 3x squared minus 1. All right. So thank you so much for listening. I'll just uh flash the questions again. Okay, you have 1 to 3. All right, practice problems 1 to 3, 4 to 7. Yeah, 4 to 7. Then 8 to 10, 8 to 10, 11 to 11 to 13, then 14 to 17, then 18 to 20. So try your hands on them and see how well you understand. Let me know how helpful this is for you. And if there's something else you haven't tried out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, why not go ahead and do that right away? Hit the notification bell also, so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join, which gives you some special privileges that you find out as you do that. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.